This mini lecture is about estimators. So let's document where we are. Last time we talked about sources of error when we're doing statistics. We talked about the concepts of precision and accuracy. And remember my analogy to throwing darts at a dartboard. What does it look like if you're throwing darts precisely? What does it look like if you're throwing darts accurately? And we also talked about computing means and standard deviations and variances of linear combinations of random variables. So today, for the first part of this lecture, I'm going to talk about point estimates and point estimators. Right? And you'll see that this is new language describing stuff that we've kind of already talked about, but it's going to introduce some new ideas for how we measure how good these estimators are. So to put this in context and to connect it with stuff that we've talked about before, remember what we do in statistics is, we have this big population and we want to make some measurement of that population to understand it. And then we do that by taking a sample of the population. Often we don't have access to the whole population, but we can have access to a sample. And then we can make our measurements of the sample. So the idea is the population has some statistic. Like the mean of some measurement. And when we look at a sample, we estimate that statistic. So this would be called an estimator. Of mu. And if I took a sample, that would be an estimate. So if I actually compute a value for a sample mean, that would be an estimate of the mean. But if I have a formula for the sample mean, that's an estimator. And the book makes this distinction too, so you can see how it talks about those. So in this case, the mean is called a parameter. It's a statistics. It's called a parameter. And it's often something that we're trying to get at. We're trying to understand a parameter. And we can calculate a parameter from our sample. So mu would be an example of a parameter. X bar is our estimator of that parameter. Some parameters that we've talked about so far in the course are the mean, the variance, and the standard deviation. Estimators that we've presented are the sample mean, the sample variance, and the sample standard deviation. So we've already defined some estimators. We didn't call them estimators, but that's what we're going to start calling them now. There's another parameter that is of interest to us, and it's a parameter called proportion. So I'm going to try to explain to you what proportion is. We've seen it before, so I'm going to connect it with ideas that you've already seen, but this is looking at it with new language and in a slightly different way. So a proportion parameters P And I want you to think of like a Bernoulli trial, okay, that has probability of success P. That means that if you do an experiment like flipping a coin, like a fair coin, that's a Bernoulli random trial with probability of success, say getting heads, of 50%. So P is 0.5. And what we would do, if we knew we had a fair coin, we'd know that our proportion of heads is going to be 0.5. But if we didn't know what our proportion of heads was going to be, the only way we could, and it was some parameter out there that we had to estimate, we'd have to think of ways that we could go about estimating that. And so we would come up with an estimator, P hat. So one way we could do that if we don't know if we have a fair coin or not. So let's write this down. Not sure if coin is fair. Okay. So think about it for a second. What could we do to estimate the probability we get a heads on this coin that we don't know is fair? So if you thought, well, let's flip the coin a bunch of times, that's what I would do too. I'd create an experiment where I flip the coin n equals 100 times, say. And then count the number of heads. And so you count the number of heads and say you get 51. Then if P is supposed to be the probability of getting heads, and we're trying to estimate that, our P hat is going to be our estimator is going to be our number of heads over 100 flips of the coin, and our estimate in this case is going to be 51 over 100, which is 0.51. So that's one way we can come up with an estimator for a proportion of times we expect to get heads when we flip a coin. So I'll give us some more examples of that in this mini lecture as we go forward. So yeah, let's look at another example of this right now. So another type of proportion, or another place where we see proportions, is when we have a random variable that's distributed as a binomial random variable. Okay. So remember, n is the number of Bernoulli trials, and P is the probability a trial ends in a success. This is the conceptual way that we talk about a binomial random variable. So if somebody gives you a process that's a binomial process and asks you what the probability of success is in P, doesn't tell you it, and asks you to estimate it, what's a natural way for you to do it? Well, let's do this in the context of an example. And let's talk about the Skittles candy. Hopefully you know what the Skittles candy are. You can look it up online. You can buy them at any convenience store in a little personal-sized bag or in bigger bags. And they're just little hard spherical candies that come in a variety of colors. And generally a bag has 5 colors. Primary colors. And one of the colors is red, so we're going to focus on red. And one of the things the manufacturer says, and I think the manufacturer is Wrigley, the manufacturer says colors are manufactured in the same proportions. So if there's 5 colors, each bag should have 20% of each color. So if each bag has the colors in the same proportions, then 20% of the Skittles in any one bag should be red. Okay. The company manufactures all the colors in equal proportion, and if they can get the candies into the bags in equal proportion, then the bag should have colors in equal proportion. But it's well known that that doesn't happen. The colors don't get into the bags at equal proportion. So if I've got a bag of Skittles candies in my hands, I'm pretty sure that we're not going to have 20% red. But let's estimate. Let's create a statistical experiment that will help us estimate the proportions of red candies in my bag of Skittles. So in this case, I'm going to say X is going to be the number of red candies I withdraw from my bag if I withdraw 10 candies. So I'm going to take out 10 candies and I'm going to ask what's the number of candies I have that are red. So my sample space here, of course, is going to be the set of numbers from 0 to 10. Those are any of the possible outcomes. And this is a binomial random variable with parameters n equals 10. Let's write it that way. N equals 10. And p equals, I'm not sure what p equals. That's kind of what I want to discover. If we were at a manufacturing site and we withdrew 10 candies from the manufacturing line, knowing that the manufacturer creates them in the same proportions, then I'd be pretty sure that p is 0.2. But with the bag I have in my hand, I'm not sure what that is. So if I want to estimate p, what I do, I take 10 candies, and the percentage, the proportion of candies that I get that are red, the number of red candies divided by 10 is going to be approximately equal to the proportion of the candies that are in the bag, right? This is one of the principles of probability that we've been talking about this semester. Okay. But this thing on the left-hand side, I'm going to call that my estimator. The number of candies I pull out divided by 10. So that's how estimators work. So if I take out 10 candies and I get 3 red, then my point estimator for or my point estimate for the proportion is going to be 0.3, which is different from 0.2. So that's how this works. That's how point estimates work. Continuing with this estimator, p hat, which is the number of red Skittles you draw out of a bag divided by the number of total Skittles you draw out of a bag, for example. Continue with the idea that x is a random variable that's a binomial NP, and that we're going to use the estimator p hat to be x over n. This estimator has uncertainty. All estimators have uncertainty. So in this case, uncertainty is going to be expressed according to standard deviation. So let's see what the standard deviation for this particular estimator for proportion would look like. Well, our estimator is defined to be a random variable x over n. N is a constant, and we talked last time about estimators or parameters or standard deviations or variances for linear combinations of random variables. And so we know this is true. And since n is, or x is a binomial NP random variable, we know its variance is n times p times 1 minus p. So doing a little algebra here, this n cancels with that n there, and we're left with p times 1 minus p over n. So that tells us that the standard deviation of this point estimator, which is the square root of the variance, is the square root of p times 1 minus p over n. All right, so that's kind of cool. We can use what we know about a binomial random variable to tell us something about the standard deviation of a point estimator for that random variable. But, Dr. Miller, you might be saying, let's use red because it's kind of urgency, we don't know p. Yeah, right. I know. That's what we're trying to estimate. Still, what does this show us? It shows us something really good. We don't know p, but we do know n. And no matter what p is, we can make the uncertainty of our point estimator as small as we want. Wrong color. Can make the uncertainty as small as we want by increasing n if necessary. And if you want to do a worst case scenario analysis, right, you can find a value of p that maximizes the numerator. Find a value here of p that maximizes the numerator, which I think you'll see is 1/2. And then choose n using that value of p. So that's the worst case scenario. Then you know that your point estimate standard deviation is definitely going to be smaller than that. So this is a way that we're going to analyze point estimators. Let's talk about bias. An estimator, theta hat for a parameter, theta is unbiased if the mean of the estimator is that parameter. This definition of bias agrees with the way we've talked about bias to this point in the course. Gives us a specific definition, however. So when we talk about bias, a lot of times we'll look at that difference. And of course we want bias to not be present. And so we want this difference to be small, if we can. But let's look at this proportion and our estimator for proportion. So if x is a binomial random variable with parameters n and p, and if we define p hat to be the random variable x over n, let's show p hat is an unbiased estimator. So that means that we just need to go up here and show that the mean of our estimator is equal to our parameter. So I'll show the mean of p hat equals the parameter that we're trying to estimate. Well, what's the mean of p hat? Well, p hat is x over n. And we've shown that the mean of a multiple of a random variable is that multiple of the mean of the random variable. We also know that the mean of a binomial distribution with parameters n and p is n times p. So here you see those n's cancel, and we're left with p. And this is exactly what we wanted to show. This shows the mean of our estimator equals our parameter. So the estimator for a proportion, a population proportion, x over n, is unbiased. So that's pretty cool. So this is an example of an estimator. How we talk about bias of an estimator, here's an example of showing that an estimator is unbiased. Let's do another example. Let x be a random variable with mean mu. I don't care how it's distributed. It's a random variable. It's got a mean. So if we let x1, x2, x3 up to xn be separate and independent trials of x. So basically they're all copies of x. So they all have the same mean. We can define the following point estimator. Call it x bar. And it's 1 over n times the sum of the results of all these experiments. This, of course, is called the sample mean. And we've worked with this before. Let's show x bar is an unbiased estimator of mu. So we need to show the expected value, the mean of x bar, has value mu. All right, well, let's do it. Let's start over here. The mean of x bar is the mean of 1 over n times the sum of all these random variables. That's a linear combination of random variables. So leaning on what we did last time, I can pull that scalar multiple out in front of the mean in that way. And then I can use the linear nature of the mean and say the mean of the sum of random variables is the sum of the mean of the random variables. All those random variables are a copy of x, so they all have mean mu. There's n copies of mu in this sum. So I can rewrite that as n times mu, and then those n's cancel, and there we go. I just showed the expected value of x bar, the mean of x bar, is actually mu. So this shows the mean, because the mean of my estimator equals the parameter it's estimating, it shows that x bar is an unbiased estimator. Okay. Sample mean is great. That's it for this mini lecture. Tune in next time for more information about estimators.